This was the very first transistor, and it was made in 1947. By 1978, the industry had advanced to integrated circuits with features just 1 micrometer large. That's 50 times smaller than a human hair, and was done on a machine that cost about $2 million. I want to replicate that capability in my own shop, so I'm going to build a photolithography machine with the goal of hitting 1 micron features. But, it's 2024, which means I can cheat and use modern technology to speedrun through the last 30 years of progress. And hopefully make it a little cheaper than $2 million. If you're new to the channel, here's a quick overview of what's going on. There are hundreds of steps to make an integrated circuit, but arguably the most important step is called photolithography. It's the process of transferring a pattern into a photosensitive resin that's on the wafer. That pattern is then used for every other step in the process of making a chip. It's basically the same idea as cameras and film emulsion, the light-sensitive resin that's used in SLA printers, or the resist that's used to manufacture PCBs. The only difference really is in size. Chips are very small, and so the pattern we put on the chip also has to be really small. I've dabbled with photolithography a little bit in the past, and the machine I made was, well, charitably, it wasn't very good. In fact, it was basically unusable other than as a demonstration. I've also done some electron beam lithography in the past, and it's perfect for really small features. I've been working on some vacuum transistors that have gaps just a few hundred nanometers wide. But my machine isn't really designed for patterning large areas. So if you watch my DIY camera sensor video, you'll have seen all the issues I had with stitching multiple fields together to form like a bigger chip. So I have 2 goals with this project. First, I really want to hit that 1 micron feature size. It's, just like a nice round number, and it coincides with a historical kind of pivotal moment in the industry. In 1978, GCA introduced the MAN 4800 DSW. This was the first commercially successful wafer stepper that used reduction optics to print patterns. And it was basically a huge jump forward for the industry at the time. So I figured the 1 micron mark would be a good milestone to aim for. Also, and this is just kind of fun, the machine retailed for $450,000, which in today's money is about $2 million, making the equivalent of a $2 million machine in my own shop. I don't know, it kind of just sounded like a fun challenge. The second goal was to write patterns over a large area. With a good microscope objective, it's actually not that hard to hit sub-micron features, but it's very challenging to do that over a wide area consistently. With those goals in mind, let's start designing this machine. The device I made a few years ago was constructed from aluminum extrusions, 3D printed components, and basically bubble gum. I kind of just assembled it as I went, and it really wasn't great. I want this new machine to actually work reliably, so it's time to fire up the old CAD program and pretend to be an engineer. I designed a frame that let us mount the motion stage at the bottom and all the necessary optical stuff at the top. It also doubles as an enclosure. Photoresist is sensitive to ultraviolet light, so there are large yellow acrylic panels to filter out anything that could expose the resist. I decided to go with a sheet metal design for this project. I've never really done sheet metal work before, but it made sense for this machine. 80/20 extrusion is a pain to work with in my opinion, and I wanted something more professional than Home Depot wood panels. Unfortunately, I don't really have any sheet metal capabilities in my shop. I have CNCs, but they aren't really designed for large sheet fabrication. Luckily, you can order laser cut parts from Send Cut Send. The process is really easy. Just design in CAD, export a DXF or step file, and upload to their online system. They also have bending services, which I used liberally on these parts to make assembly a little easier. I'm a Fusion 360 user, and Fusion has a pretty decent module for modeling bent parts. You punch in the bending parameters that Send Cut Send provides for their different materials, and then you just start creating bends and flanges. I fired the parts off to Send Cut Send and got to work on the optical system. This is basically a DLP projector in a dev kit form from Texas Instruments. There are a few main components to this. There's a lens section here, which we'll be removing because we don't need a projection lens. There's the DMD chip inside of the device, and we'll see that in a minute. And then there's a bunch of complicated optical components down here to couple 3 high-power LEDs into the projection system. So one of these LEDs, the blue one, we'll be replacing with a UV LED. And we'll keep red and green as they are because we can use those for inspection and alignment purposes. So the next step to do is pull off the projection lens and add in our own adapters so we can start adding optics that we want in front of this system. And now I'm gonna roughly get all the optical components in place just to make sure everything fits and see if I need to make any more cage plates or if some of these don't work or whatever. So we've got a lens, a beam splitter, another lens, microscope objective, and this is a camera. Okay, I'm gonna take a pause for a minute to explain the optical system, kind of like all the different things going on here. So the heart of the system is a digital mirror device, or a DMD. These are made by Texas Instruments, and you'll see them on DLP projectors. It's basically like a matrix of little micrometers that can be individually addressed, flipping them back and forth, turning it essentially on and off. So when they're flipped one way, they send light to the projector lens, and when they're flipped the other direction, it just sends light off into nowhere, and you get a dark pixel. But the trick here is we can take the projection optics, remove it, and put some kind of reduction optics, like a microscope objective. And that will project a pattern down to a small size on your substrate. And this is basically what's called a maskless lithography machine because we don't have any mask. We're just making the pattern digitally on a computer and displaying it with the DMD. This is a very well-established route to take. There are hundreds of academic papers that use this. Real commercial lithography machines will actually use a DMD internally. And there's even a bunch of YouTube channels like Sam and Huygens Optics that have done this as well. So this is nothing new. I'm just doing it again, kind of with my own take on it. My original plan was to build a direct write laser machine, very similar to the first one I built a couple years ago. But I changed my mind when I ran across the Hacker Fab group. This is a group of like self-organized students at CMU that are building an open source lithography fab. So it's all the things you need to build a chip, spin coaters and litho machines and process development. It's all being documented and put online. So I decided to go their route and pick up a DMD similar to what they are using. My system ended up being quite a bit different than what they have, but it was really helpful having all this stuff pre-documented. So if you're interested in open source litho, definitely go check it out. They're doing some really cool stuff over there, and it's all accessible online. The actual optics are pretty simple. UV light is projected onto the DMD, which is toggling those mirrors on and off to form an image. This generates a diverging beam that comes out, and we collimate it with a lens. It then hits a beam splitter. Most of that light continues straight down into a microscope objective, which focuses it down onto the substrate. Some of that light is absorbed by the photoresist, and some of it bounces off and goes back the way it came, hits the beam splitter again, and is redirected into this horizontal arm. Another lens takes that beam and focuses it onto a small USB camera, which we can use for alignment and focusing. And that's basically it. It's pretty simple as far as optics are concerned. We also have to replace the blue LED with ultraviolet LEDs. I've never used solder paste before, so please forgive the crimes I'm about to commit. They soldered up a bit wonky because I don't know what I'm doing, but they work fine, so whatever. Then we need to drill some holes in the base plate so that the DMD can be mounted to the rest of the frame and assemble the whole optical engine. A week or so later, the Sen-Cut Sen parts have arrived, and it's time to start assembling the frame itself. The frame is made from 1/4-inch thick mild steel, while the 2 door side panels are made from a slightly thinner cold rolled steel. And then there's like a back panel, which is just a really thin aluminum. A 1/4-inch might have been a little overkill, but I want it to be super sturdy because any vibrations or movement of the frame will directly impact the resolution. So I kind of messed up the design of this, but I think it'll be recoverable. Basically, there's a bow to this bottom plate. That's just the nature of this type of metal. So this is just A36 mild steel. It's not the fault of the laser cutting service. That would happen if you bought this sort of plate straight from the metal distributor. So what I should have done is put a vertical section here, bent upwards, and then the same on the front to turn it basically into a box. If we look at this piece, this is basically what I should have done. I needed a bend on the left and a bend on the front, and that makes this surface remarkably flat for being, a piece of just bent sheet metal. Luckily, having it fully assembled seems to constrain the structure a fair amount, and it's relatively flat. To get these parts ready for painting, I first had to deburr all the laser cut edges. Laser parts are way cleaner than plasma cut, but there's still a sharp burr that needs to be removed. SendCutSend offers deburring services for a very reasonable rate, and in retrospect, I really should have opted for that service. Deburring all these parts on my little bench polisher took forever, and honestly, I didn't do a very good job. I also had to degrease all the surfaces before painting, especially the mild steel, which is oiled to prevent rusting. Then it was time to prime and paint the panels. This was also something else I should have let SendCutSend deal with. They have powder coating services, which would have resulted in a much nicer paint job and let me focus on other parts of the build. While that's drying, let's take a look at the motion platform. This delightful bit of equipment is an XY stage from Zaber. And honestly, it's the reason I decided to work on this project in the first place. It's a linear motion stage with 1 nanometer encoders, and the specs are honestly just wild. 50 nanometer step size, 500 nanometer repeatability on movements, a max speed of 750 millimeters a second. That's like almost a meter per second. Well-characterized pitch and yaw errors with interferometry data for each stage, and it's all controlled with a really nice Python API. Now, full disclosure, this stage was donated to the channel by Zaber. They are not sponsoring this video, they don't get to preview or make any editorial changes, and I'm allowed to say basically whatever I want, good or bad. But frankly, I have nothing bad to say about it. It's just like a really nice bit of kit. I'll talk about the stage a little more later once we start using it, but for now, let's focus on what goes on top of the stage. So the stage was originally made for a microscope, which is why it has the hollow part in the middle. But I'm using it obviously for an upright microscope, so we need some kind of adapter, which is what this is, to just provide a flat surface for us. Next we'll mount a Z stage. Now we are going to mount the rotation and wafer chuck stage on top of this. For the rough setup, we've got a stepper motor, a housing, which goes on top, another housing, which sits there, and then like a spindle unit, which fits down inside of that. Huh, that's interesting. The top 2 holes are fine. Bottom 2 definitely do not match up. Nope, that was definitely my fault. I modeled the stepper motor hole spacing incorrectly. So we're gonna do the age-old fix of drill out 2 of the holes to make them a little bigger, and hopefully it'll line up then. Alright, we're gonna try the less age-old approach of using an end mill in a drill. Oh yeah, that'll do. I mean, it's not beautiful, but and rotate that. This is such a terrible design. Who came up with this? Okay. And the O-ring on top. And the kinematic mount. Here's a cross-section view of how it all works. The stepper motor directly drives the rotation stage. To also pull a vacuum on it, there's a hole down the center of the shaft and 4 cross holes which open into a chamber sealed by 2 O-rings. The O-rings allow the shaft to spin while also keeping it airtight and pull a vacuum. Finally, there's a kinematic mount on top composed of pins and ball bearings, plus a few magnets for preload. This allows me to take the top surface on and off easily without worrying about alignment. You just throw it back on and it'll click into place. So now that we have all the individual components done, we can finish assembling the whole machine, put it all together. All right, so we have it roughly assembled, and I'm not displeased, but there's definitely some problems. Most of it stems from just lack of experience working with sheet metal. This is not flush because there's a cap head screw in the way and I neglected to make a cutout. The paint is starting to chip off already because there should be some clearance between the lid and the frame. I'm currently holding the lid open with just a piece of aluminum stock, which obviously is not how this is supposed to function. I need to get a gas spring to help lift the lid up. I forgot that the stage is bolted to the bottom of the frame with a through bolt and a nut, and that means there's a bolt and a nut sticking out the bottom, which means it can't sit flush on the platform. I totally forgot to put some bolt holes on this side up here, which means that this acrylic piece flexes downward when it's in its resting position because there's nothing supporting it and it's pretty thin. When we close the lid, we've got a few problems here. First of all, there's no handle, and if we come around to the side, we can see that it's not actually at a right angle because, again, there's a cap head screw in the way. Next, we need to mount the projector to the frame and all the optics onto the projector. Cool, so I have it all set up over here. It's plugged in and running, and it's controlled off of my laptop at the moment. We are not at all aligned, so the next step is getting all of the optics aligned and configured so that this displays an actual image. Well, I'm not going to bore you with all the details here. There were many hours of fiddling and tuning and dialing and adjusting all of these components to get everything aligned and working together. We are making progress. So under the microscope at the moment, if we zoom in, you can see I've just got a random PCB just for something to look at basically. And if we pop over to the webcam, you can see, well, maybe you can't see. I don't know if you can see, but basically we've got a checkerboard pattern coming from the DMD, and then there's texture in all the spots that aren't black, and that is the PCB. So if I move the stage a little, you can see it moves under it. This is really cool. This means it's working, and I'm really excited right now. So I've got the motion system wired up and basically working, not programmed to do anything intelligent, but I've got the rotation stage up here on top rotating and the XY stage, XY staging. So if we run a quick test program, we should see the stage rotate here. Okay, and now the stage itself will center and then start stepping through a grid pattern. And there it goes. Pretty cool. Okay, so after all that work, I think it's time to try some test exposures. The procedure is similar to what you've seen in past videos. Photoresist is dispensed onto a glass substrate. It's spun at a few thousand RPM, forming a thin film on the surface. It's then baked on a hot plate to remove any extra solvent. I typically scratch a corner to give me something to focus on, and then put it in the machine and hit run. My Python code then displays a test pattern for different lengths of time, moving around between each different exposure. After that's done, the pattern is developed in dilute potassium hydroxide, and if all goes well, we should have some microscopic patterns to look at. I checked them out under the scanning electron microscope, and the results are encouraging but mixed. Some are pretty good. There's like nice crisp features with small details. Other patterns are frankly just plain awful. Blurry lines, uneven development, just like all around bad. So it took me a while to understand what was going on here, but I eventually realized these were mechanical inaccuracies that were causing the objective to go in and out of focus, depending on the location. And so the further out of focus the objective is, the more blurry the resulting image. So there's a few options. The wafer chuck itself could be not actually flat, and so that'll show up when we move in X and Y. Or the rotation mechanism could have some run out, so it kind of like wobbles as it rotates around. If I had a motorized Z stage, some of this would be easy to fix in software, because we can basically refocus at each new location. But I don't have a motorized Z stage, it's just manual, which means we'll need to fix it mechanically as much as possible. So I've got an indicator on the wafer stage, and we're gonna rotate it around and see what it looks like. Yeah, so it looks like it's got about 4/1000ths of runout, either in the spindle itself or this platen on top, which is not great. Yeah, so if we move the stage in X, is maybe 1/10 of deviation, which is great. But if we move it in Y, there's, I don't know, maybe 3 thou across the whole thing. And we know for a fact that the stage itself has excellent linearity. So all of the error here is in the stack up. So something about my rotation stage, vacuum chuck, manual stage, all of this on top of the XY stage is causing the error. And look at it this way. Now we have the error in X and a little bit in Y. It's probably mostly from this mechanism here. There's just runout in how this is spinning. And there might be a little bit of error from the kinematic mount, because honestly, I didn't do a great job. You can even kind of feel it here. There's some rocking motion. Because I think probably this O-ring is a bit too large for this setup, so it's not making good contact on the balls. That should be an easy fix though. I think I will, so there's the high spot. And if we take it to the other side, whew, that's 2 thou. Yeah, so there's all of our error. Probably from sanding that down by hand. So I've got 2 stacks of shims down on this bottom plate. I've got 5 thou of shim on these 2 corners, tilting the whole thing that way. I spent more time shimming the setup, so now everything is within about 1/2 thou. And we can see in the Y, I'm about 1/10. And if I lock the stage and move to X, we're about 1/10, 2/10, depending on where you take it. So hopefully this is enough to keep us in focus. 1/10 is 2.54 microns. After a truly ridiculous amount of adjusting and many, many more test runs, I've gotten consistent resolution down to 2 microns, with a few notable caveats. First, adhesion of the photoresist to the glass wafer is proving troublesome. The resist I'm using is super old. It expired in like 2018, and so I'm guessing it's just losing its adhesive quality over time. This means patterns can have pretty small features in the resist, and they develop pretty well and look really nice and crisp, except for when it develops all the way down to the substrate. As soon as that happens, it starts to peel off the surface and whole areas get washed away. I can fix that with adhesion promoters or a thin layer of metal, but it really complicates the process by adding a lot more steps or pretty toxic materials. The second unfortunate caveat is that I'm still having a difficult time hitting focus reliably. So despite all of my work mechanically trying to get everything square and parallel, it's still struggling to hit focus over a large area. Okay, fam, we need to have a chat about this machine, because things are not going quite as well as I had hoped. It is 9:38 a.m. on a Sunday morning, and I'm here working on this, trying to get everything dialed in. I think we've just hit a bottleneck as to like the ultimate resolution that I'm gonna get with the current setup. We need to reconfigure the rotation and Z stage so that it's a little more adjustable, probably motorized. The optics themselves should probably not be hung off the projector like this or cantilevered off to the side. It needs more adjustment mechanisms. Basically, the whole setup needs to be just kind of reconfigured. which is a lot of work. Problem that I'm having, the main issue, there's a lot of problems. The main issue is that the depth of field of this high numerical aperture objective is too shallow. And with my manual Z stage, we just can't hit that across a whole stitch field, even if it's relatively small. So the fix is just to have a bigger depth of field. And you do that by using a lower magnification objective. Now, of course, with a lower magnification objective, that means you have a limit to the resolution you can hit. I don't have the numbers off the top of my head. I'm sure I can put them on screen. But basically, this guy could probably hit 800 nanometer features, whereas a 4X objective, I think, is limited to like 2 or 5 microns, something like that. So plan B is basically to write masks using this maskless system. And then once we have those masks, we can put that into some kind of reduction system to take the mask and put it down to our final size. Ultimately, that means if we could hit, say, 10 or 20 micron features with this objective, which frankly I think should be really easy, we can take that 20 micron feature, use a 10-to-1 reduction lens, and make a 2 micron feature on our final substrate. So this is obviously a lot more work because now we have to build a second machine and go through the whole process of tuning and dialing in all the parameters for that and building masks, which is probably not going to be super easy in of itself because large things are always harder than small things, which is counterintuitive, but that's just like how this works because process development sucks. But we will have a more reliable system on the maskless side, and it has a nice symmetry because like this is essentially how the semiconductor industry works. You make a mask, and then you use that mask to put in some kind of wafer stepper that reduces it to a small scale. And there's cool things we can look at in the future, like how you optimize masks for diffraction limited imaging and off-axis illumination and all this other like really kind of esoteric stuff. So this is mostly just me convincing myself that this is a good idea and that I should stop what I'm doing and go build an entirely separate machine instead of fixing a machine that is honestly working pretty well, just not well enough. So I don't know if you think this is crazy or not. You should probably tell me before I start. Yeah, so I decided to build the mask projection system. What can I say? It seemed like a more fun option at the time. This time around, I tried to design the components to be reusable. For example, the two side panels are symmetric, so they can both be used on either side, and the support brackets are all identical, just rotated into new positions. Ordering the side panels twice rather than two different side panels is like 20 or 30% cheaper, and so it really makes sense to reuse components where possible to help drive the cost down. Optics are all down at the bottom on this machine and held together by 3D printed assemblies. I decided to print these because the mechanical requirements of the system are quite a bit less stringent than the other one, and it's just faster and easier to print things sometimes. The reduction lens that I'm using is an old Zeiss lens. It's a 10-to-1 reduction dedicated lithography lens, and it was probably made sometime in the late 70s. I picked it up on eBay a couple years ago, and honestly, I've just been wanting to use it in a project for a while, which is maybe one of the reasons I decided to go this route. Who can say? I don't know this for sure, but there's a good chance this lens was probably used in one of those GCA MAN 4800 wafer steppers that I mentioned at the very beginning of the video. It's impossible to know exactly, but this lens was used in those machines, and I think Zeiss made them specifically for that machine at the time. The mask is held by a printed component attached to an XYZ positioner. This will let me adjust the mask by small amounts if I need to for alignment purposes. And the positioner itself has a magnetic base, so it clamps onto a steel bracket, which is attached to the back of the enclosure. The light source slides back and forth along these two steel rods. The red alignment light goes on the left, and the ultraviolet light goes on the right. But let's talk about that light source for a moment, because it's a surprisingly tricky topic. In a perfect world, we would have 100% collimated light passing straight through the mask, and it would be generated from an infinitely small point source. Traditional light sources were typically mercury or xenon lamps, filtered to remove all of the non-ultraviolet components. The output was then collected and homogenized and recollimated through a series of lenses and mirrors. A more modern option is to use an array or a matrix of ultraviolet LEDs. The problem with this is that LEDs have a pretty diverging cone of light that they generate, so you need to collimate that, and the best way to do it is to put a single lens above every single LED. But I decided to take a totally different technique from this paper. It uses a stack of thin film light modifiers to generate a quasi-collimated beam of light. First in the stack is a diffuser to help homogenize the light. I took the glass that was in my UV lamp and I just hit it with some sandpaper to make a ground glass diffuser, and that does a great job. Next up are two orthogonally stacked brightness enhancing films. These are plastic films with little pyramid shapes, and due to internal reflections, light mostly escapes in the forward direction. The rest of the light bounces around and is recycled until it finds a way out. So it's a way to enhance the light output in kind of a preferential direction. Some of the light still escapes at more extreme angles than we'd like. So on top of that are two orthogonal layers of privacy film. This is like the stuff you put on your laptop to keep people from looking at your screen on an airplane. So they restrict the amount of light going off axis. And it's basically a clear plastic with thin vertical strips of black plastic inside in kind of like a grading pattern. And so light that's going straight escapes just fine, but light that is moving at an angle will hit those black strips and be blocked. The final result is a beam of light that is mostly collimated. It's kind of hard to capture on camera, but there's very little light coming from any of the sides, and most of it is traveling forward. Now, the big downside to this is that you lose a lot of light energy going through this stack of modifiers. I don't know the transmission specs off the top of my head, but say each one is 80%, 85% transparent. That's a lot of light that gets lost when you have 5 of them stacked on top of each other. So it remains to be seen if this will work well or not. I'm cautiously optimistic. Worst case, we can just let it expose for longer if we need to. Finally, there is a beam splitter that sits on top of the lens and a camera to focus and align the mask. So hopefully you can appreciate from the state of chaos here and lack of fully assembled machine, things haven't gone to plan. The long and short of it is that I had originally intended to use the optics that came with the little camera. This is like a small compact zoom lens, and from initial testing, I thought it would be okay to provide the alignment through the beam splitter. It's not. It doesn't work. There's just no way to make it work given the current arrangement, or probably ever. It was just a bad idea. I tried a variety of different optics that I have sitting around. I've got a bunch of different stuff in my parts bin, and I found a few arrangements that would maybe work with this particular setup, but it wasn't ideal, and really I should just stop wasting time and redesign all of this and do it again. Okay, so here's the new revision. Obviously, it's all in metal now, which is, just makes everything easier. But there are a few distinct changes from before, mostly around adjustability. So you can see that the bottom stage where the wafer goes, or the substrate, has gained 2 more stages. So now this is an X, Y, Z, theta stage. The lens is directly above it. And then we see up here the alignment optics setup. We have the beam splitter, which sits on top of the lens using still just a 3D printed mount. I don't love this. It doesn't fit very well. So I'll probably replace this at some point, but it's okay enough for now. We'll take the light, bounce it into the alignment optics that go into the camera in the back. And you can see that that is just a microscope objective, kind of used in reverse. So it's taking the image that's coming out of the lens down here and magnifying it onto, or really demagnifying it onto the sensor of the camera. This setup also has 3 degrees of freedom. So there is a translation stage over here to move the objective kind of in Y, and that allows us to focus the image from the substrate onto the sensor. So this is basically a focusing movement. And then there is an X translation, and around the back there is a Z translation with that one. And X and Z allows us to change the position that we're aligning to. So like we've got the mask up here, and as we change this one and this one, it will move this objective around and let us focus on different parts of the pattern that we're aligning to. Everything can be moved in basically all relevant degrees of freedom because I just wanted to work and I'm tired of messing around. And then obviously, since it's in metal, everything's just a lot more rigid, and we shouldn't have to worry about stuff flexing and moving just because, you know, polymers aren't great for this sort of setup. So yeah, let's throw it in the machine and see how it works. Okay, so predictably enough, there's something wrong that needs a new component. So this arm that holds the objective doesn't allow the objective to get close enough to the sensor. So we need to replace this part with a new one, and luckily I've already made it. It's a new design, but it gets everything a little closer. There we go. There is another problem, but this one's a much easier fix, and it's that the diameter of this microscope objective is basically the same diameter as the C-mount threads that hold the microscope camera in place. And I didn't think that was a problem because I thought there was enough relief on the inside here to allow it to get in focus, but it's not quite enough. Luckily, microscope objectives usually have a part of the housing that comes off. Sometimes it's the whole thing, sometimes like this one, it's just the front half. Take that off. You can see now it's much thinner, this diameter, and that actually will allow it to go inside of that bore and get us to our critical focus. There-ish, if I remember correctly. Here's how it works. Super simple. We take a mask and we put it in the mask tray. This is a test mask I made with my fiber laser a couple months ago, so the features are enormous, but it'll be fine for alignment purposes. Next, we bring the substrate and the mask into focus using the red light. If there's an existing layer, we would also align it to the mask at this step. Then we switch on the ultraviolet light and let it expose. And that's it. It's super easy. With all of that tentatively working, we need to go back to the maskless system and make a mask. For mask substrates, I'm using these large plates of glass coated with about 100 nanometers of copper. That's thick enough that you can't see light through it, so it's opaque, but the copper dissolves easily in ferric chloride, so it just makes processing easier later. On my third attempt, I got something approaching halfway decent, and it's certainly good enough to test with to start. If we look at the mask under the microscope, we can see a few issues that we'll need to correct in the future. The stage is holding great positioning accuracy because it has those, 1 nanometer encoders on it. But there are still some misalignments if you look closely, and this is actually due to a rotation in the optical system. It used to be a whole lot worse, but I applied some rotational calibration, and now it's just slightly off. But we can see that each field is rotated ever so slightly, causing a mismatch between adjacent fields. It's something I need to fix, it's just not bad enough for me to worry about at this point. You can also see some of these, like periodic triangles in the corners. This is from uneven exposure. There's a bit of tip-tilt misalignment in my optics, and so the corner is slightly out of focus, which means the ultraviolet light is a little more diffuse in that area and it doesn't expose quite as quickly. And ultimately, when it gets developed, it doesn't develop as quickly either. And more generally, I just didn't develop long enough, so this whole central region didn't quite clear. And it's kind of like foggy because there's still copper left over. I miscalculated my pixel to micron scale, and so I think the smallest line width is probably going to end up about 2 or 3 microns rather than the 1 micron. So that's something we'll have to fix in future masks as well. But like I said, it's good enough for testing, so let's take it over to the reduction system and see how it does. Hey, not bad, honestly. There are some limitations and problems here, but we knew about those already. Like the minimum feature size is about 2.5 microns due to the mask being scaled a little incorrectly. And the features in the middle are kind of garbage because the mask was kind of garbage there, but generally it turned out really well. I do notice there's a bit of fall off around the edges where probably the light intensity isn't quite as uniform as it is in the middle. That's something we might need to fix, but we can also maybe just fix that with longer exposures. I don't know, that's a TBD. But it definitely looks promising. So let's go make a newer, better mask and try this all again. The system is not working anymore. I can't get the device to boot up fully. It gets kind of stuck during the boot phase. And it took me a while to figure out, but I think it's because the UV LEDs are dead. They died somehow. I don't know why. This power cable goes to the red LEDs, and this goes to the blue channel, which is now the UV channel. And if we check them both with a diode test, shows 0.6 volts in one direction and 0 volts in the opposite direction, which is what you'd expect from a diode. So that's good. And if we check the blue LED, or the UV LED rather, we get 0.071 volts one way and 0.071 volts the other way. So that's cool. Basically, from what I understand, I don't know electrical engineering, but I think that means the diodes are shorted open because we were seeing a voltage in both directions. And unfortunately, the UV LED is way up in here. There's a heat sink, and then behind that heat sink is the LED itself. And there is just no way to get to that without disassembling the whole thing. We have to pull the board off, then we have to pull the optics off, then we have to pull this cover off to get to those LEDs. So the whole stack has to get torn apart. And then we have to replace the LEDs, which I don't have on hand, so that's cool. I do, however, have these LEDs. These are 365 nanometer wavelength as opposed to 405, which is currently in the system. I got these because I thought it'd be fun to try 365, not realizing that the pad is a different size, so it doesn't actually fit the circuit board. So these have just been sitting around. So I could use these without having to order new ones, but that means I will have to instead order a new PCB. Okay, well, that kind of sucks, not gonna lie. I did end up making those PCBs and I just received them, but I don't know. I feel like this is a natural stopping point for the video. And frankly, the prospect of tearing apart the whole optical system for like the 100th time fills me with existential dread. Did I hit my 1 micron goal? Well, not really. Close, but 2 microns is not 1 micron, so we can't really say we did. But I do have some real photo masks from the late 70s, and they're interesting to look at. The resolution patterns go down to 2 or 3 microns, but the actual features are enormous. I mean, they're like huge. Chips might need the finest resolution for certain areas, like the transistor channels, but for the most part, most things on a chip are actually pretty big, all the wiring and vias and contact pads. So I'm gonna personally count this as a qualified win. I built 2 machines, a maskless photolithography stepper and a 10-to-1 reduction system, and I now have the tools to build features on par with 1980, which you can do a lot with that. There's a lot of really cool chips out there from that time period. Big thanks to SendCutSend for sponsoring this video. Funnily enough, I'd actually ordered all of the sheet metal parts with my own money because it just seemed like the right approach for this kind of project. And it only occurred to me about halfway through that SendCutSend might be interested in sponsoring. So I reached out to them and, well, here we are. So yeah, as far as sponsorships go, this is one that I absolutely do recommend because I actually use my own money on it. Having access to laser cut sheet parts and especially the sheet metal bending is really huge for me. Like, I would love to add the tooling to deal with sheet metal stuff here in my own shop, but frankly, I don't really have the space for it, and I don't think I would use it enough to justify the expense. But I'm more than happy to have SendCutSend do it for me, and it was quick and easy to get the parts. I don't think I'd really want to deal with the logistics of 1/4-inch thick sheets of steel anyway. A full-size sheet is about 600 pounds and nearly $700, plus probably like twice that in freight fees. So really happy to just let SendCutSend do that for me. Both times that I ordered, the parts were here within a week, and shipping was free, which was a nice perk because metal parts get kind of heavy, and especially that first batch, which had the 1/4-inch thick steel, that was not a light package. So free shipping was just kind of a nice extra surprise. It was a lot of fun learning how to design and work with bent sheet metal, and I'm pretty excited to use this capability in future projects. So yeah, if you are working on a project that could benefit from sheet metal, I highly recommend checking out Send Cut Send. It was super easy and the parts were great. As a final closing note, keep an eye out for a companion video to this one. I know this one has gotten very, very long, but despite that, I had to cut a lot of really interesting technical details about the motion and the kinematics and compensation and the optics, all the kind of really in the weeds details that are interesting, but just didn't fit here. So the plan is to edit together kind of an engineering cut of all the extra details and footage that didn't make this one, and just do it kind of, low production value, stream of conscious, looking at a webcam sort of thing. And that'll be out in, I don't know, a week or 3, whenever I recover from editing this one. All right, cool. I think that's all I got for you. Thanks for sticking it out to the end, and I hope this was interesting. I'll see you next time.